Welcome back. I'm excited today because we get to talk about two of the most famous effects that come from special relativity, time dilation and length contraction. And I'm also excited because I get to talk about one of my favorite parts of my favorite effects, and that is that we're going to end this video with two different mathematical expressions that look very similar to each other. And that leads us to the lesson that says, just because things look the same doesn't actually mean that they contain the same physical importance. And so even the names of these two effects, time dilation and length contraction, have a certain symmetry in the language. But we find out that the way that these two effects come to be actually are quite different. One of them seems to be very real, something that we can easily measure, whereas the other one is really a consequence of the first. Okay, so let's start with time dilation. I can think about this as dealing with the problem of having two different reference frames. I have a reference frame that represents the lab, that's the black frame on the left, and I have the reference frame of something passing through the lab, right? So I'm going to call that the physicist reference frame, and that's going to be blue. Now, we know enough about space-time diagrams to sort of think about what the trajectory of the physicist looks like in both of these reference frames. So in the physicist reference frame, what does the physicist do? Well, she just travels along the world line that represents the CT prime axis, right? When we are in our own reference frames, what we do is we stay at the origin, right? No matter what our reference frame is doing in other people's reference frames, we're always at the center of our own universe. But if now I look at the path of that physicist in the lab, well, that physicist can be traveling through the lab at some velocity with respect to the lab. And so that blue line in the physicist reference frame that's traveling perfectly upward along the CT prime axis is now moving at some angle in the lab frame. And therefore, although in the physicist frame, she's just traveling through time, in the lab frame, we're traveling through both space and time. And therefore, we've traversed some distance, which we're going to call delta x, and some distance here, which we can call c delta t, right? And so this just goes back to that fundamental principle of special relativity, that you always are traveling, right? In the case of in the physicist frame, the physicist is just traveling through time, but in the case of the lab frame, you're traveling through both space and time. But I can still compare things between these two frames because I have things that are inherently frame independent, namely the space-time interval. And so to try to compare what's happening to the coordinates in the lab frame to what's happening to the coordinates in the physicist frame, I'm going to say that I'm going to take the two of my events along this world line, and I'm going to say that the space-time interval between those two events has to be the same. So I can calculate that both in the lab frame, where I have a separation in time and a separation in space, and I can compare that to the physicist frame, where I just have a separation in time. Okay. Now I have three sort of unknown things here, right? I have delta t, I have delta x, and then I have delta t prime. Of course, knowledge of the velocity of the physicist in the lab frame allows me to get rid of one of those, right? Because I know that all velocity is it tells me the relationship between delta x and delta t in some given frame. And I can also relate that back to the dimensionless velocity beta, which is velocity over c, and I can get a relationship now between delta x and delta t. This is one of the most powerful relationships that we've been using in special relativity. The velocity tells me the relationship in some reference frame between separation in time and separation in space. So all I have to do, plug that into the left-hand side, and now if I look at this expression, everything on the left-hand side has delta t's in it, and everything on the right-hand side just has delta t primes. And so what I really have is I have an expression that compares the difference in delta t as measured in the lab frame with delta t prime as measured in the physicist frame. Right? So a colloquial way of saying that might be I'm able to relate changes in time in the lab frame with changes in time in the physicist frame. And as I go to sort of infinitesimal changes in time, this thing probably represents a relationship between how time ticks, the differential difference in how time ticks in each one of these two reference frames. Now, this expression, though, could use some tidying up because I can make new definitions to make it look a little bit prettier, and I can also try to think about which one of these two times is sort of the more fundamental time. First, I'm going to just make the definition. This combination of the square root of 1 minus beta squared actually appears a lot in special relativity, and so we give it its own symbol. We call it gamma. Although gamma really is 1 over the square root of 1 minus beta squared, and you'll see why in a second. Okay, this gamma factor then tells me, well, how different is my speed from the speed of light, right? So if beta is really small, gamma looks like 1, and now delta t is equal to delta t prime. Relativity isn't so important. But as beta approaches 1, the square root of 1 minus beta actually approaches 0, and it's hard to talk about how close you are to 0, but if you do 1 over the square root of 1 minus beta squared, now we have a number that gets bigger and bigger and bigger as beta approaches 1. It actually gets bigger without limit, right? So as I get closer and closer and closer to the speed of light, gamma gets bigger and bigger and bigger. It's often called just the relativistic factor, right? Because it really tells me how relativistic the problem is. On the right-hand side, though, now I look at that delta t prime, and I actually say to myself, there's something special about that, right? After all, that is a unique measure of time in a reference frame where the object, or the observer, or the physicist in this case, is only traveling through time, right? So that's unique. There are no other reference frames in which the physicist is only traveling through time. Every other reference frame, the physicist is traveling through space and time. And so that time is now measured in a reference frame where all of the events are happening at the same place. And if we're looking at the time measured in the coordinate system where all of the events are happening in the same place, then we call that time the proper time. And the word proper here really comes from that idea of uniqueness, right? It's the time as measured by something happening in the same place. And so we usually call it, with the Greek letter T, tau. And now that time is special because, after all, it's the time you measure, right? If I'm carrying my watch with me, then I'm always measuring the proper time because my watch is always with me. It's always at the origin of my reference frame. And so the proper time is the thing that our cells know about. The proper time is the thing that you experience while, you're waiting in the doctor's office or you're waiting on the bus, right? It doesn't, as long as you're carrying the clock with you, the thing that you're measuring is the proper time. And so now, because the proper time is this thing that's unique, it's most convenient or most traditional to redo this expression so that I'm solving for the time in some other reference frame, delta t, in terms of the proper time and the velocities. And of course, that just means taking this expression and turning it around so that I have the time measured in any reference frame and how it relates to the proper time. And of course, this expression now is beautifully succinct, right? It tells me, well, how does a clock tick in the lab compared to how does the watch of the physicist tick, right? And since gamma is always going to be bigger than 1, what I've actually found is that every other clock is going to tick faster than the clock that the physicist is carrying. And that's why it's called time dilation, right? Because all other times are longer than the proper time. The proper time is, by definition, the shortest possible time. Okay. And this effect is real, right? Because although we derive the expression for proper time in terms of something traveling at a constant velocity, if I have a path now that's a little less constant, say this green path here, well, that's a perfectly valid world line, and the physicist carrying a clock along that world line is going to be able to measure some proper time. Now, if I calculate the proper time along that world line using now an integral expression, right, I can actually say, well, what is the time along that green line, which is the proper time of the physicist, and compare it now to the laboratory time, right? And I can actually come up with a comparison between how long did it seem to take in the lab versus how long did it seem to take the physicist, right? And now we come to some of these beautiful paradoxes that we'll talk about in class, but at the heart of time dilation is something very physical, something that you can actually measure because you can calculate now what the coordinate time is and compare that coordinate time to the proper time along any given path. Okay, so that's time dilation, but what about length contraction, right? These things always seem to come together. Well, length contraction, rather than talking about how long did something take, sought to answer the question about how long is something physically? What size is something if it's moving past you at a relativistic speed? But to interpret this question of how long is something, we have to do something a little bit more clever than we did with time, because after all, we carry things around with us that measure time, right? With maybe watches or maybe cells or some experience, right? Time is something that's inherent to an observer. If I want to talk about how long something is, well, now I have to go to my space-time diagram, because length is something that appears in a direction really perpendicular, or at least not parallel to how we experience time. And so if an object is passing me in the lab, so now I have an extended object, and it's passing me at some velocity through the lab, what does it mean to measure the length of that object? Well, the things that I actually measure is I measure the time at which the front of the object passes me, and I measure the time at which the back of the object passes me. And that time then tells me, well, how long do I think it took that object to pass? And I can also measure the velocity with which that object is passing me. And so I can use those two pieces of information to infer how long the object is. Okay. Now, when you first measured objects, you used rulers and you used tape measures, but that doesn't work in a relativistic sense, right? Because these objects can be, in principle, passing by me very, very quickly, right? But when I want to measure the length of an object, what I'm really doing is I'm saying, how long did it take that object to pass me, right? And if I know how long it took and I know the velocity, then I can infer the length of it from those two ideas. And so now when I'm talking about how long does an object appear, I'm actually changing the question from one of what's the spatial extent of the object to how long did it take. I'm asking a question about time. Okay? And so length contraction, no matter what we do to think about it, is always going to be a consequence of how long did it take. It's always a consequence of time. And so to calculate it now, we're going to have to actually compare two different times, right? So I'm thinking about the time that I'm experiencing in the lab, trying to measure the length of the object, and I'm thinking about the time that's being experienced by the object as it's passing by me, right? Now, the only thing that we really agree upon, because space and time are things that are coordinate system dependent, is really the velocity that we see each other passing, right? So if the object is passing me with some velocity v, then the magnitude of the velocity that the object sees is also v, right? So the velocity is something that we can now use to compare between two coordinate systems. So in the lab, I say, well, this velocity, which is something I can measure, must be related to both the length of the object, which I'm just going to call L, and how long it took that object to pass me. At the same time, if I go to the object's reference frame, I can say, well, the lab is passing me with some velocity, so I must be passing the lab with the same velocity v. But I know that I'm L naught long. So L naught here is the length of the object as measured by the object, and therefore sometimes, well, most of the time we call this the proper length. And since we like definitions, we'll extend that definition to mean, the proper length is the length of the object as measured in a reference frame where all of the object is at the same time, right? So that's the rest reference frame. But the velocity, according to this object, this stick, is going to be its proper length divided by how long did the stick think it took to pass me, right? So just looking at these two expressions, I know that the velocities are going to be the same, right? Because if I'm passing the object and the object is passing me, we agree on the magnitude of the velocity. I want to know how long it looks. The stick knows how long it is. So the thing that we're left to compare is actually how long did it seem to take in the lab versus how long did it seem to take to the stick. And I can rearrange that, solve for L, and I get that L is equal to L naught times this ratio of the time taken in the lab to the time taken in the stick's reference frame. And of course, now I'm back to this idea of what's the relative change in the clock that the stick has versus the clock that the lab has, right? And now I can use my time dilation formula to relate those two times, but I have to ask myself, who's actually measuring the proper time? And I think this is the most confusing part about length contraction, because we've already said that the proper length is something that the stick owns, right? Because when I measure the proper length of the stick, I'm talking about where are all of the events at the same point in time. But when I want to compare between these two reference frames, only one of the reference frames can be measuring the proper time. And of course, the definition of proper time is the reference frame in which all of the events are happening at the same location. Well, as the stick is passing me, where is the location the same, right? At which of the two observers is measuring everything at the same location? Well, the stick has a bunch of different locations. The front of the stick is inherently at a different coordinate than the back of the stick. So the reference frame that's actually measuring the proper time is the reference frame in which all of the stick, namely the front and the back, hit the same location in space, and therefore it's the lab that's measuring the proper time, because I'm standing still in the lab, and I'm watching the stick pass by me, and therefore I have the right to measure the proper time, because it's in my reference frame that everything is happening at the same location in space. And so I can plug in what I know for the time dilation formula, because the time experienced by the stick is the dilated time. And that's actually going to throw this gamma now in the denominator of this expression. And that's why I say that the length that I infer in the lab is actually shorter than the proper length. And I'm going to try to be really careful with that language. I'm not saying the stick is shorter in my reference frame. I'm saying that I'm inferring that the stick is shorter, because the thing that I'm really measuring is the time, right? So I know the velocity, I know how long it took, and I am then calculating what the length of that object must be. And the fact that the length of the object is different, or the calculated length of the object is different, depends on the velocity. That is all tied into the fact that it's actually the clocks that are different in these two different reference frames. And so we can't forget that when we talk about time, when we talk about length contraction, what we're really talking about is we're talking about time dilation, because the lab is the reference frame that's measuring the proper time. And now we get to this point, we have two very similar looking mathematical expressions. On the left-hand side, I have a coordinate time is bigger than the proper time. And on the right-hand side, I have that a length is smaller than the proper length. And we want to jump to conclusions about the symmetry between these two objects, but really they're very different when it comes to what's the fundamental measurement. Because the fundamental measurements that we're making are really of time. And so the time dilation formula is the important one. That's the one that tells us how do clocks differ depending on their relative velocities. The length contraction formula is a consequence of time dilation. Okay, so here's what you want to take home. Time dilation measures coordinate time, right? That's I can calculate delta t based on a proper time. And that's an effect that's real, right? Because if I go to paths now that are more complicated, or if I go to paths that, leave and then come back, I can calculate proper time along that path and actually compare it to time taken in a different reference frame. Whereas length contraction is something that's always inferred. It's something that's calculated by watching an object pass by you and trying to calculate its length based on how long it took to pass you and what its velocity was.